Hello and welcome to another video in my PyTorch deep learning series. Today we're going to be covering the logistic regression. Now I'm going to add in a little bit more complexity to this one. I'm going to throw in a few different activation functions as well as a hidden layer. And those activation functions are going to be both ELU as well as the sigmoid function, which is pretty common when you're going to be working with logistic regression. With that being said, if there's anything in this video that is a bit confusing, I've covered it in other videos within this PyTorch series. I'm slowly building up the complexity of the models that we will be coding out together, but I will be explaining everything line by line. So if this is your first video in this series, you should be able to go through all this code and hopefully understand it at the end of this video. All right, with that being said, let's start coding. All right, so the first thing we're gonna do is we're gonna import a few different libraries. That way we can grab in our data and also start using PyTorch. So let's do that. First, we're going to import in Torch, which allows us to use most of the stuff with PyTorch. Then we're going to import in torch.nn as nn. We'll be using this a little bit later when we create a class within our code. Then we're going to import in numpy. So import numpy as np. And then from scikit-learn preprocessing, import in our standard scaler. So standard scaler, and scaling your data is very common when using PyTorch. So that's why we're going to use our standard scaler. I think I did a video on the scikit-learn series on that side of things. Up next, what we're going to do is from scikit-learn.model selection, import in train test split, very common over there. And lastly, what we're going to do is we're going to bring in a data set. So from scikit-learn.datasets, I'm going to import in the make classification, and essentially you can make a classification data set as the title states. Very easy. So make classification. I'm just going to shift and enter. It runs a cell, it creates a new cell down below. Awesome shortcut. And what we're going to do first is going to create some device agnostic code. So what we're going to do is device equals torch.device. Then you're going to put over here CUDA. And we're going to say if torch.CUDA is available, right? Else CPU. And I'm just going to run the code on the CPU because I'm kind of lazy and don't want to change things up. But if you want to run on your GPU, welcome to do so. And Google Colab has two different options on that. All right, so now what we're going to do is we're going to essentially create our data set for make classification. I'll explain a little bit. So what we're going to do is we're going to set our X and our Y. We're going to say that's going to be equal to make underscore classification like this, right? And then inside over here, we're going to have a bunch of different parameters. So you can set your samples that you want. I'm going to go super basic and just do 1000 like that. Then you can set your features. Let's do 17 today equals 17. Okay. Up next, what we're going to do is say how many informative features do we want to have. So I'm just going to say 10. Then we can have redundant features. Let's say n redundant equals 7. 10 plus 7 is 17, right? Then we're going to say n classes. We have to set this equal to 2. That way you have binary classes. And then you set your random state. I'm just going to say 21. Why not? And that's going to create our data set. And boom, just like that, just a few lines of code, we are off to the races. So I'm going to build out a few new cells down below, and we are going to continue to move forward. It's going to be helpful a little bit later on if we declare our samples and features. We can get this through x.shape. So just to show you what x.shape prints out, right? 1017. So let's set this up. We're going to say n samples and then also comma n underscore features, right? We have 1000 samples, 17 features. We're going to see that's equal to x.shape like that. And boom, we have that saved. So, and now what should be very common if you've watched some of my scikit-learn videos or you've done any machine learning models at all, we're going to set up our X train, X test, y train and also our y test. We're going to set that equal to train test split. Funny enough, I remember the first time I coded this and I was like, man, this is a long line of code. Test size equals 0.2, and now it's super ingrained into my memory. We're going to do random state equals, say, 18 on this side of things. All right, we have that there. Now we're going to scale our specific data. So I'm just going to say SC equals our standard scalar. And one of these PyTorch videos, I actually did it by hand. So much easier just to do standard scalar like this, but it's good to show the other way sometimes. So we're going to do sc.fit transform, and then also you don't have to do the math behind it. Although I like math, but I look at efficiencies. We can write it in one line of code. We can write it, right? And then we're going to do x test over here, and it's not going to be fit transform. I made that mistake a long time ago. This one's just going to be a transform. So SC standard scalar, x train, x test, and then make sure x test is also in this one over here. So train with train, test with test. Again, scaling our data is important. You want better results. So that's in here now. And now what we're going to have to do, so we're going to have to convert essentially our numpy arrays to torch tensors. Now, luckily within PyTorch, this is cake. So what I'm going to do is write one line of code. We're going to duplicate it a few times and we'll make a few modifications. Let's do that. So what I'm going to say is xtrain equals torch.from underscore numpy. I'm going to throw in here xtrain like this. Then we're going to do .type. We're going to change this to torch.floats 32. And then we're going to .toDevice. And then like that. And we should be good. So we're going to copy this a few times. 2, 3, 4. I'm going to just change this to xtest. There's going to be nothing else different for the x's. The y is going to be little. So we're going to say y train, and then let's set our y test. And then I'll explain what we're going to be changing here in a second. It's not too bad. We're going to reshape these y tensors. And the way that you do that is you can just put .view. So view over here, -1 and 1. Essentially, we want to have this to be one specific column. Again, that's our final output. And also remember, we're going to be doing a binary classification, right? So that's what we're going to be taking a look at. Our .view -1 to 1, -1 automatically resizes this based off of the one column. Proper term is reshape, but there we go. Make sure you do it for y train and y test. Run this and you're good. So now what we're going to do is we're going to create our specific class that's associated with this. So let's code this out. I'm going to call this class Logistic Regression. Okay. And then we're going to inherit over here. So if you remember torch.nn, essentially we're grabbing our nn.module. So just put nn.module over here. And it is time to go to work on this class. So the first thing that we're going to do is do a special dunder method. So it's going to be called init over here. I've talked about this in my classes video. I recommend you learn a little bit about classes before you jump into PyTorch. I had to teach myself stuff like that because I haven't really used them outside of PyTorch, at least on my day-to-day job and what I've been doing on the channel. So we're going to do our self, which is going to be that specific instance that we do when we create our class instance. And then we're going to have our input features. And the reason why we're going to have our input features, if you remember over here, we have our end features, right? We're going to have it very similar to that side of things. Okay. So now we're going to put a colon. We're going to go another line. We're going to super. And what we're going to do is we're going to super our logistic regression. So logistic regression, like that. And then we're going to put in self over here. Now we're going to do dot. We're going to do another init over here like this. Okay. And what we're going to do is we're going to create our first layer. We're going to say self.linear. It's going to be equal to nn n.linear. And the first thing we're going to do is put our n input features, right? What we put into our specific model. And then we're going to put 20 over here, because I'm going to be building out a few layers associated with this, okay? Now I'm going to do a self.linear again, and I should label these. So this one's going to be linear 1. This is going to be linear 2. It's going to be equal to our nn.linear. So let's put nn.linear in here. Now we're going to put 20, and what I'm going to do is put 1 here at the very end. Remember, we want to have only one output. That's why we created this view and reshaped the -1, 1. We want to have one output, right? We're going to be putting in 17 input features, and we want to have one final result. That's what our binary classification is going to look like, okay? Now what I'm going to do is I'm going to put an activation function over here. Now, I've already tested my code with a few different activation functions, and I found ELU performed pretty well with this specific model and also the data set. So I'm going to be using ELU, but I will have a video out. I don't know if it's going to be out before this or after, talking about many different types of activation functions, 10 in general. So I will recommend watching that video when it is out on the channel. But we're going to put self.elu over here, and it's going to be equal to nn.elu, like that. So it should be all capital. So now what we need to do is define our forward pass. So it's def forward, and you'll see this in all of your models as well. Let's put our self and put our x in over here. And then what we also need to do is put a colon, because I did not do that. Then we're going to set our output over here, and we're going to say x equals self.elu, and then we're going to put inside over here self.linear 1, right? And then we're going to put our x in over here, okay? And then now what we're going to do is set our y predicted. So y predicted equals our torch. Now we're going to put a sigmoid out over here, which is going to be very common with logistic regressions. And then what we're going to put over here is self.linear. And then I'm going to put linear 2 actually, and put our x back in over here. So let me explain how this code works. Once I put over here the return y predicted, and I think we should be good. All right. So essentially what we're doing is we're throwing our x in over here for this self linear 1, right? Outside the self elu. Then over here, we have our self linear 2 with this x like this. And then we have our y predicted, and then we return our y predicted, okay? So let's run this specific code, and we are good. And one thing I do want to call out before we continue to move forward, this order might be a little bit confusing why I did this, and why our ELU is over here before our second linear layer when it's technically not in this order. It's pretty common to do within PyTorch. ELU is going to add non-linearity to the specific model, and that's why we put this right after our linear 1 in here within this forward pass, right before we get into linear 2. And we don't have to call our sigmoid in over here. You'll see some of these quirks as you work on a few more specific models. All right, now it's time to call our model, which essentially is the self that we keep on doing, right? So we're going to say model equals, and we have our logistic regression. You can literally just copy this, and this is going to take in one input, which is our features, right? And if you remember earlier, our n features like this. So just copy your n features, paste it right over here, or you can type it out if you're not lazy like I am. And then you can just put device in here. And again, if you want to use your GPU or not. And I do have an issue over here. And yeah, so this needs to be capital L's. So make sure those are capital L's over here. I think that's the reason why I had my error, but let me just double check. And it is, right? You will have a lot of coding errors like that. All right, so now we're going to define a few other things really quick before we do our training loop. So first is we're going to do our learning rate. and this is something you can tweak and see what performs best. For me, I found 0.1 worked really well with this specific model, so that's what I'm going to do. Now you're going to set up your criterion, right? And that's going to be for your loss. I'm going to do .bce loss, and that's binary cross entropy. Now, cross entropy, I have a video on here on the channel already on. It's very common for classification. BCE is for binary, so that's why we're going to use it in this specific instance. And lastly, you want to set up your optimizer, and I'm just going to do this to torch.optim, and then we're going to do SGD, and SGD is extremely common, and then we're going to set our model.parameters like this, and then we're going to say our learning rate is equal to learning rate, which we have above over here. Great. And now what we can do is we can set up our training loop. So the first thing that we need for any training loop is epochs. This will tell you how many times that you're going to run through your training loop. So I'm just going to do something pretty easy and say 1,000, right? We have 1,000 samples, so we're going to do 1,000 epochs in over here. So you're going to just do this basic for loop. So for epoch in range, and then you just put over here your number of epochs, right? So it'll go essentially 0 through 999 because we're going to stop at 1,000 in this one. This is an optional parameter, but I see it used a lot. So just put model.train in over here. Now we're going to do our y predicted. It's going to be equal to model, and then you're going to throw in your x train over here. Okay. Then what we're going to do is calculate our loss. And that's going to be equal to our criterion. And again, we're using BCE over here. So make sure you put your criterion. Then you're going to put first your y predicted, and then you're going to put your y train. So we're going to pretty much look at the difference between our training data set, right? What we fully expected, and then our prediction based off of essentially what we wrote over here, right? And now what we need to do is we have 3 lines of code, which you're going to have to memorize because they're essentially in everything. So we're going to have to do our backward pass. So that's going to be loss.backward like this. Okay. Then we're going to say, we're going to step our optimizer. So optimizer.step like that. And then we're going to 0 grad it. So optimizer.0_grad like that. Not ZEO, but 0 with an R. And then now we should have some type of print statement. So since we're doing 1,000, I'm just going to print out every 100. So I'm going to say if epoch plus 1, I have this over here, 100 equals 0. So essentially this will print out every 100 with, that's what this line is taking a look at, right? 101 right here, right? It's not going to equal 0. It needs to be exact, like 100, 200, 300. So that's how this kind of works over here. We're going to do our print statement. Put an F string in here. We're going to say epoch, and then we'll put over here epoch plus 1. Put a comma, and we'll say loss equals, and then we'll just put in here our loss dot item, which where's that from a tensor, and then we'll just round it like 0.2f. Not too concerned with that, and then I think we should be good. Let me just change a little bit real quick because we don't need to have that over here. So epoch equals, which will be our epoch, loss equals, I think we should be good with this over here. And typo there. So, ooh, there we go. So epoch 100, 200, 300, 400, 900, 1000, and then our loss. You can see, like, as we train our model more and more, our loss continues to go down. So at 100, it started 0.39, 36, 34, 33, and we have it down to 0.25. So if we increase this over here, it's possible this would be a bit more accurate, and we can test it. And accurate, I mean, we're going to be decreasing our loss over here. I'm going to take a look at the specific accuracy at the very end. We're going to put it in evaluation mode, but let's see. Let's put like 5,000 here and see if we can actually get something a little bit better, right? And look at that. We are getting way better at 5,000. Our loss is 0.09. Again, feel free to tweak this how you specifically wanted, but I just wanted to show you if we increase our epochs, we get a pretty good loss score over here with 0.09. So now I want to take a look at the evaluation, and this is going to be towards the end of our code. I will explain everything over again, but we're going to put our model in evaluation mode. So we're going to do with torch.inference mode over here. And I've seen also inference mode versus torch no grad. So I'm not 100% sure what's the best one to use. I've seen both used in code, so I've used both as well with some of these videos. So I don't think there's that much of a difference, to be honest with you. But we're going to put y.predicted equals model. And we're going to put over here x tests, right? Then we're going to say y.predicted CLS equals y predicted over here dot round. Okay. Then what we're going to do is ACC equals y predicted CLS over here dot EQ. Then we're going to put in our y test. We're going to sum this. So sum over here. Then we're going to divide by our float. And we're going to say y. Put over here our y test shape. And we'll throw an A0 over there. And then this works. Print F. We'll put over here accuracy equals ACC. And we'll run this to 0.2F. And 0.89 accuracy. And to explain essentially what we're doing, right? So we have our Y prediction, which we're going to do this time through X test. Then we're going to take a look at the class on it, right? When we're going to be specifically rounding this. So 0 or 1. And then we're going to take a look at our accuracy. So we have our 0 or 1 over here, right? This is a Boolean comparison. This compares it to the Y test, right? And if they're both the same, it'll be a 1. If not, it's going to be a 0. So we're summing that. And then we're taking a look at the shape, which I believe we did 20% for the testing size. So this would be 200. And then we're printing out our accuracy, which is this over here. But let me explain some of the other code once again and how we did this. So up first, what we did is essentially import in a bunch of different libraries. Then we created device agnostic code. We created our data through make classification in scikit-learn. Then we took a look at the shape of our X, right? So number of samples and features, we set that to shape because we had 1,000 samples with 17 features, which we defined right here, right? Samples and also features. So I guess you could have technically hard-coded it, but I think it's better just to do X shape. Train test split, we also scaled our data. Then we moved everything over from arrays over here on the numpy side of things to tensors. And then we created this logistic regression over here. And essentially we inherited from nn.module, right? So we have this code over here, super logistic regression. Then we have two linear layers, linear 1, linear 2, with essentially 20 over here. And we have 1 as our output because on this side of things, right, we're taking a look at a binary classification. And then we have an ELU over here. Now this code over here, very common to put an ELU in between two linear layers. And then I wanted to have a sigmoid here at the end because it's very common with logistic regressions if you want to have a better result here at the end. And then we return our specific Y predicted. We create our model, again, our features, which we defined above over here, which was 17, but better just to have this as a variable. We again to device. Then we define our learning rate, our criterion. BCE loss is very common for binary side of things, especially with this logistic regression that I created. We use the optim.sgd. We always throw our model parameters in here. We set our learning rate. And you can put this over inside over here, or you can just put your variable out over here. Then we created our training loop. So you put your epochs here at the top, or I guess you could have technically put it over here in this cell. Either way, you'd run a basic for loop for epoch and range. You don't have to do this, but I just put this in here for training purposes. Y predicted equals model. We put our X train in here. We find our loss. Then we do these 3 backward step 0 grad. This is just a print statement. Again, feel free to do what you would like. And then we set our model over here. We can use torch no grad or inference mode. We set an evaluation over here. Then Y predicted, right? This time we take a look at the X test side of things. We round this over here so that way we can set it to our class 0 or specifically 1. And then we compare our test to our specific prediction over here. They match, we sum that, and that way we get our specific accuracy. And then we just print out our accuracy over here, which was 0.89. So hope you found a ton of value in this video and you're able to build out your logistic regression. You're one step closer to mastering PyTorch and understanding deep learning. With that being said, if you did find some value in this video, you subscribe to the channel. It's 100% for free, but it does allow YouTube to share this video as well as the channel and other videos to people that are learning data analytics or data science. And if you want to learn even more about PyTorch, I have a full video playlist right over here.